Hello everyone, my name is Daniel Segrest, and this week I had the Rankine cycle. So thermodynamics is the study of energy, and heat is often used as a source of energy. William Rankine was one of the founding fathers of thermodynamics, and he helped to develop the Rankine cycle, which is equivalent to the Kelvin scale but in degrees Fahrenheit instead of centigrade or Celsius. But most importantly, the Rankine cycle is a theoretical process still used today for virtually all of the production of the world's electrical power. So the objective of this lab is to understand the operation of the Rankine cycle and to measure the relevant data as well as calculate important parameters associated with the performance of the Rankine cycle. So in the setup here we have the component diagram, which is going to consist of four main components. We have the pump, the steam generator, as they call it, which is also known as the boiler. We have the turbine and the condenser. You can see that there are certain parts that are numbered 1 through 4 as spaces in between these components, and those will be referenced in this diagram. So here we have the pressure, specific volume, and temperature entropy diagram. The PV and the TS. You can see on the left that this 2 to 3 line basically shows a constant pressure as well as the 4 to 1 because the cycle is going to be moving like this. So here we have our boiler and at the bottom is our condenser. 1 to 2 is going to be the pump. You can also see here that because we're going to be pumping liquid water, the specific volume changes just a tiny little bit, but it's mostly considered incompressible, whereas these processes are considered to be isobaric. Additionally, if we look over at the TS diagram, we can see that the pumper is considered to be isentropic, and likewise the turbine is also considered to be that way. So the first law of thermodynamics for steady-state devices will show that we have a few equations for the pump, boiler, turbine, and condenser when it comes to how much heat or work is being done in that component. So these are the first law derivations for those particular relations here. Just kind of go over this briefly because in the lab we will be actually doing this. And then when we combine all the equations for the entire Rankine cycle, we have Qin minus Qout minus, as a quantity, work of the turbine minus work of the pump is equal to 0. So the heat input into the boiler minus the heat rejected by the condenser minus, as a quantity, the work the turbine does minus the back work that the condensate pump return pump does. And at the bottom, we have how that all comes together mathematically. So our thermal efficiency is the work of the cycle divided by the heat that we added times 100 to get that as a percentage. So we have our enthalpy values that we'll get through our steam tables put along the side here. So the Rankine cycle is not a real cycle, it's an ideal cycle. Because of that, we don't account for some of the losses that we actually have. For example, friction, which also means that there's going to be a pressure drop. Additionally, it's not adiabatic perfectly, so we do have some heat losses to the surroundings. We'll also, in this particular lab, have some water that's just lost through leaks. And I wish I could make this a little bigger, but this is about as good as I can get it on my particular system here. This is kind of a setup of what we're going to have. You can see we have the condenser tower here, and there's a turbine. I tried to highlight these, and our boiler. There's a lot of other stuff going on in this picture. One of the main things we'll be checking out is the voltage and also verifying that there's no leaks when it comes to safety from this propane tank right here. So the lab procedure I'm going to go through pretty quickly. Initially, everything's going to be off. We're going to be draining and refilling the apparatuses of and with water. The requisite valves in the open or closed position as prescribed by the lab manual. We also need to make sure that we've connected the computer DAC system and the liquid propane fuel, but we haven't turned it on yet. Then during startup, we're going to turn the computer on. That's what happens first. Obviously, if we did have a fuel leak, we wouldn't want to have any sparks happen first. So after the computer's turned on, we're going to turn our regulator on for our fuel and then check for fuel leaks. So if we hear any hissing sounds or rotten egg smells, we know we have a leak and we need to shut it off immediately. Then we're going to turn the burner on and observe the combustion blower and verify that it's on, purge the fuel lines if we need to, verify that the burner is lit within 45 seconds of selecting the on position, and then we're going to monitor the boiler pressure. Preheating commences, and this takes about 10 to 7 minutes. And that's going to allow the boiler to rise to approximately 110 degrees psi. 110 psi. Then we're going to open the steam admission valve and turn on the load switch. We adjust the load rheostat so the voltage does not exceed 10 volts. Then we are going to monitor boiler pressure until it falls to approximately 40 psi. After that, close the steam admission valve. The pressure will begin to rise again. Allow the boiler pressure to rise to approximately 110 psi. While maintaining 110 psi boiler pressure, the steam admission valve is to be opened slowly at a speed which maintains approximately 110 psi of boiler pressure. Try not to let it increase above 110. The guidelines did say that this was approximate, but we're trying to keep it inside of there. So once the turbine begins to spin, the generator will produce electricity, and we will continue opening the steam valve until the voltmeter shows full-scale detection or 10 volts. The load switch should be selected to on. We're going to adjust the load rheostat to maintain 0.2 amps and 6 volts. When reasonably steady state is achieved, we're going to proceed further and begin our experimental run. The time should be noted. Also, we need to set the sight glass on the upper bezel to the current indicated water level to monitor water drops that may occur during the run. We'll use the steam admission valve to maintain a steady state during the run. As we monitor the water level, it must not fall 2.5 centimeters, so about an inch from the bottom of the sight glass, or damage may result. Then after the data collection, proceed to shutdown procedure. We're going to be measuring the condensate collected and the water which was consumed, and that's basically by removing the condensate that built up in the turbine and then filling up the boiler all the way, emptying our container, and then releasing the water that's in it back into an empty container until we get back to where our sight glass said the water was, so we can figure out how much was used. So whenever we start up our computer in Windows, we'll open up the Rankine cycle software. To start logging data, very simply, just click on the Log Data to File button. Then we'll put in a file name, press OK, and then when we're ready to stop, just click the End Data Log button. We'll import that data into Excel and save it, and then we'll be making some graphs in Excel. There's quite a few things we need to graph. These are all going to be versus time. We've got fuel flow, boiler pressure, turbine inlet and outlet pressures, as well as temperatures, the generator DC, amps and volts, plus the turbine RPM. So we also need to determine one point in time that steady state was pretty much going on for sure to evaluate the system. And then at that point, we're going to be recording the atmospheric pressure, the boiler fill amount, the fuel flow, boiler pressure, boiler temp, turbine inlet, outlet pressure and temperature, steady state condensate amount, and the steady state boiler water that we used up. Quite a few things to keep track of. We'll be analyzing this. We're going to compare the heat flow out of the boiler to the measured liquid propane gas flow to the burner. We'll find the work rate of the turbine and efficiency of the generator. We'll find the heat removed from the condenser and its efficiency, as well as the system mass flow rate. Then, using those steam tables we all love from our thermo textbooks, we'll gather state data for different areas of the system and finally calculate the thermal efficiency of the cycle as a total efficiency. And then here is my prediction of what the thermal efficiency could be. This is assuming that our max steam temperature is 400 degrees, and an ideal cycle, all these units are going to be in BTUs per pound, since we're using PSI, and I came up with a theoretical value of 32.9%. In reality, I expect it to be closer to around somewhere between 20 and 25%. Okay, and here are my sources. Hope you guys are doing okay out there. Thanks.